This is part 5 of my lecture on parametric tests for comparing means, in which I'm going to be looking at how we test for agreement. We can compare a measured value with a known fixed value. If we're given a true value of a quantity that's known with good precision, this is a measurement that has been made and is well defined, and we have some available data, a measurement that we've made ourselves of the same quantity, and we've also assessed the standard error, determining how precise our measurement is. What we want to do is to test whether this measurement is in agreement with the given value that is well known, and the statistical test we'll use is the 95% confidence limit. In order to apply confidence limits, we think of the measurement x with a standard error s, represented by an error bar like this. The line in the middle represents the mean, and the vertical extent of the line represents one standard error on either side, above the mean and below the mean. So x plus or minus s, x is the value in the middle, plus s above it, minus s above it, representing the range of standard error. However, our 95% confidence limits are greater than that, because we know that for a normal distribution the 95% confidence limits are plus or minus 2 standard errors either side. So the dashed arrow representing the 95% confidence interval is twice as big as the error bar representing the standard error. If we represent a known value x0 as a line here with no error on it at all, because it is a precise, well-defined value, we want to know, does our 95% confidence interval include x0? If it does, so x0 lies within our confidence limits, then the measurement agrees with the known value. If it doesn't, x0 lies outside the 95% confidence limits, then they're in disagreement. Let's take an example using the half-life of technetium-99m. We know that the true value for the half-life of technetium-99m is 6.02 hours, determined with good precision. Let's suppose we've made our own measurement, and we've measured it to be 6.15 hours plus or minus 0.07. That 0.07 represents our own determination of the standard error of our measurement, how precise we think it is. And we mean by that 0.07 is the standard error of the measurement. So the question we want to ask is this measurement compatible with the known value of 6.02 hours? We're going to assume that the standard error is normally distributed, and we're going to determine our 95% confidence interval using the normal distribution. So we've shown graphically here that the size of the error bar, 6.15 plus or minus 0.07, represents one standard error above and below the measurement. So it extends from a middle point of 6.15 up to 6.22 and down to 6.08. I've also shown on there the true value of 6.02. Now we know for a normal distribution the 95% confidence limits are plus or minus 2 times the standard error. The standard error is 0.07, so twice the standard error is 0.14. So 6.15 minus 0.14 is 6.01, and 6.15 plus 0.14 is 6.29. So our 95% confidence limits extend from 6.01 to 6.29, and that does just include the true value of 6.02. So the measured value is in agreement with the accepted value. 6.02 is within our 95% confidence limit. Now, another thing that we might like to do is not to compare a measured value with a precisely known one, but to compare two measured values. So we're not given any particular data, but we have two measurements of the same quantity, each with its estimated standard error. And we want to test whether the two measurements are in agreement with each other. Once again, we're going to calculate the 95% confidence limits, but this time the confidence limits for the difference between the two numbers, because if the difference is compatible with 0, then the two measurements must be compatible with each other. So if we have a measurement x1 with a standard error s1 represented by an error bar x1 plus or minus s1, and x2 with a standard error s2 represented by an error bar x2 plus or minus s2, then the difference x1 minus x2 has got a standard error s. The question is, how big is this standard error of the difference? Well, you might think we just look at the standard error of s1 and the standard error s2 and add the two together. Unfortunately, we can't add standard deviations, but we can add variances. And if you remember, the variance is just the square of the standard deviation. So we can say s squared, the total standard error, is s1 squared plus s2 squared, the sum of the squared standard deviations of the two individual measurements. Then, having done that, our 95% confidence limits for the difference will be x plus or minus 2s, where s is this combined standard deviation. And then once again we ask, does that confidence interval include 0? And if it does, the measurements are in agreement, and if it doesn't, the measurements disagree. Let's have a look at an example of that. We can suppose that we have some data from renograms, because a patient has had 2 renograms to measure the relative function of their left kidney. The first renogram gives 38% with a standard error of 2% for the relative function of the left kidney, and the second measurement gives 33%, again with a standard error of 2%. So the question is, has the relative function really fallen from 38% to 33%, or is this just random statistical error? The statistical test is to calculate the 95% confidence limits for the difference to see whether the two measurements really disagree. So if we plot it graphically like this, we can see the first measurement is 38 plus or minus 2, and the second is 33 plus or minus 2. And although those are 5% apart, which seems quite a large difference, and indeed the error bars don't overlap, which might make you think that they must be distinct, remember we have to use 95% confidence interval, not just the standard error. So the difference, 38 minus 33, is 5. The relative function appears to have changed by 5%. But the standard error of that difference, remember, we take the standard error squared and add those. So the standard error of the first measurement is 2, and the second is also 2. So 2 squared plus 2 squared is 4 plus 4, which is 8. The square root of 8 is 2.8. So the standard error of the difference is 2.8. So the difference is 5 plus or minus 2.8, and we want to know if that is compatible with 0. Remember, the 2.8 is the standard error, and we want to know the 95% confidence limits, which are twice the standard error. So 2 times 2.8 is 5.6. 5 minus 5.6 is a minus 0.6. 5 plus 5.6 is 10.6. So the 95% confidence interval goes from minus 0.6 up to 10.6, and that does include 0. So those two measurements are quite compatible. They do agree. Despite the fact that the error bars don't overlap, the 95% confidence limits do include 0, so there is no significant difference between the 38 and the 33 with these measured standard errors. So the relative function hasn't changed significantly, at least from a statistical point of view. So that's how we can use statistical tests to see whether there has been a real change in measured parameters that we routinely perform in nuclear medicine. And that ends this part of the lecture on testing for agreement.